Good morning, everyone. I want to welcome you to our informational hearing this morning and thank you all for being here. We'll begin with a roll call.
Bloom.
Here.
Gordon. Here. RnT.
Here.
Patterson. Williams.
I'd like to welcome Assemblymember Stone, who, of course, as many here in the Capitol do, has an abiding interest in this issue and asked to attend today. Thank you for being here, Mr. Stone. And again, thank you all for being here for this special climate change hearing. As we've discussed before and I've brought up, our climate is changing, and this poses a serious threat to our environment, public health, and ultimately our way of life, which, as extreme a statement that might be, it could also be an understatement. Of course, how quickly and how severely this threat impacts us largely depends on how quickly and aggressively we meet the challenge. Over the next few decades, significant reductions in greenhouse gas emissions will be necessary to avoid the worst consequences of climate change. When we think about taking action over decades, that is not commonly our time frame here in Sacramento. So it really, I think, this issue requires us to think about things in a much different way. Mitigation efforts will touch nearly every aspect of California's infrastructure, planning, and investment. We've already experienced with water infrastructure, where approximately $2 billion has been appropriated for drought mitigation in the past 2 years, along with a $7.5 billion water bond passed by the voters. We've witnessed and experienced two very large investments to deal secure water supplies in the face of changing weather patterns. Just the tip of the iceberg. Even our addressing the drought is going to take more resources, more time, more effort. And without question, California has made significant strides in confronting climate change. We passed AB 32 in 2006, spearheaded efforts to reduce emissions from passenger vehicles, and we've established the first renewable energy portfolio standard in the country, just to name some of our efforts. But this is not enough, which is why we are now in conversations to set lofty goals to reduce petroleum, further increase our renewable portfolio and energy efficiency goals, and set a higher bar in reducing our greenhouse gas emissions under the leadership of our governor, who is, as you all know, very engaged on this issue. Unfortunately, even if we do our part and meet whatever goals we set, we still have our challenges. Here in California, we can't legislate the behaviors of other states or the international community, but we can lead by example, and I think that is something typically California has done a good job of. And we can hope that those successes will be adopted or expanded upon by others. Much like the old civil rights call to action, if you're not part of the solution, you're part of the problem. Today we're going to hear from two leading scientists from the Lawrence Berkeley National Laboratory and other experts who will let us know if we are part of the solution, not the problem, maybe a little bit of both. But in making this assessment, our panelists are going to discuss the latest projections, future risks and impacts of climate change, as well as new research that models all major California policies in order to assess their combined effect on reducing California greenhouse gas emissions. This conversation, I think, is extremely important for us to have here in this committee. We are so caught up in allocating money to address a problem, sometimes we forget to think about the problem itself and process what that means in terms of how we allocate our funding. So this is an opportunity for us to step back from our weekly funding and budgetary responsibilities and think about this issue a little bit differently, talk about it in a somewhat different context. Now, after our panelists have finished, at the end of the hearing, and after committee members have asked their questions, we are going to open the hearing to public comment. And I would encourage all of you to step forward. What I would like to do is discourage you from the great temptation you will have to address your cap and trade funding requests. I know that is one of the favorite topics here in this committee and even in the Capitol. We are going to have a hearing next week. You'll have an opportunity to do that. But I would like to, so while I'm discouraging you from doing that, I would like to encourage you to ask questions that the panelists who will be sticking around and listening to public comment will have the opportunity to discuss and answer during the roundtable portion of our discussion at the end of the hearing. Our next hearing is going to be on April 15th, and again, I encourage you to bring your cap and trade issues with you then. And with that, I'd like to ask if any of the members here on the dais have any comments they would like to add. Welcome, Mr. Williams. Thanks for being here. And I would now like to ask our first two speakers to step forward. We have with us today, and we're very honored to have Dr. William Collins, who's an internationally recognized expert in climate modeling and climate change science. He's a senior scientist and head of the Climate Sciences Department and director of the Center for Integrative Modeling of the Earth System. That, of course, is at the Lawrence Berkeley National Laboratory. We also have Dr. Jeffrey Greenblatt with us. Dr. Greenblatt has been involved with modeling pathways for California's low-carbon energy future since 2009, publishing a number of studies, including a recently published analysis of greenhouse gas policies, something that I think we'll be hearing about this morning. Welcome, gentlemen. Thank you both for being here. Take it away.
Thank you, Chairman Bloom, and thank you, committee members, for the invitation and for the opportunity to speak to you this morning. I want to talk to you about the future of California's water, and this is based on work that my colleagues and I have done as lead authors of the most recent Intergovernmental Panel of Climate Change Assessment, the fifth assessment report that was released a couple of years ago, and also the National Climate Assessment that was just released last year. So the work I'm going to show you has gone through an extensive amount of peer review and represents the input not only from Berkeley Laboratory, but also from many other universities in California and around the country. And it's a privilege to present it to you. There's going to be sort of a darkness before the dawn flavor to this talk, so just please be aware of that. I think we need to look squarely at the challenges that climate change poses to our water supply and then talk perhaps about how we might begin solving that in collaboration with one another. I'm going to start by reviewing briefly the present, and I'm sure everyone is aware of our present situation, but it is a challenge. We're fortunate to have resources deployed both on the ground, in the air, and in space to look at this issue. And the changes in California's snowpack are so evident that they're clearly visible from space. These are two images taken from a NASA imager that my group and I use extensively in our own research. These contrast the snowpack in January of 2013 on the left and the snowpack in January 2014 on the right. I was looking for January 2015 and couldn't find it when I was preparing this talk, but believe me, it looks very much like the image on the right. A dramatic decline in snowpack. 2014 also saw some of there's a striking image of Mount Shasta from the same time period with essentially no snow on its peak. So this is visible now from space, not just from the ground. This animation shows what the normal snow water equivalent, which is what you would get if you melted all the snow and turned it into a swimming pool of water, how much you should have. And it's on the order of 20 to 30 inches worth of water, so close to about a yard of water would normally be present in the Sierras at this time. At the moment, that number is down in the range of inches. It would probably come up just barely to your ankle on this same scale. So the IPCC, this Intergovernmental Panel on Climate Change, has now concluded that the declines in snowpack and the earlier peak in snowmelt runoff are likely due to global warming. They're now prepared to actually backstop that statement and say that this is a clear consequence of the fact that the planet is getting hotter. Now, if we want to circle back around to why the planet is getting hotter, I'm happy to do so, but I'm not going to deal with that in my talk just now. The drought is projected to continue over most of the American West. So there are portions of the country, fortunately, where it's actually going to wind down or even decrease. Those are to the east of us. And this projection that I'm showing you is from the National Oceanographic and Atmospheric Administration, the federal agency that's really charged, of course, with monitoring our climate, sort of for operational purposes. And the brown region shows you where the drought is likely to persist or, in fact, perhaps intensify. And you notice that's over most of the American West, except up in Washington and around the Cascade River Basin. So they're saying essentially that the prospects for relief between now and midsummer are relatively low. For obvious reasons, we're exiting the winter monsoon season in California. And this has had big impacts on our reservoirs and lakes around the country. These are pictures, courtesy of an article that appeared in the Atlantic Monthly last year. So kudos to the Atlantic Monthly for taking these pictures. I'm sort of focusing on Shasta Lake, which is well north of us, and Lake Oroville, which is just due directly north of us, both of which in August of last year were at 30% of their normal capacity. And there are lots of pictures in this same article that show the houseboats nearly high and dry. I have colleagues in my department who have family up at who have boat docks where essentially the boats are left stranded, etc. So that's the current situation, and I think it's fair to ask now whether or not this particular event, this particular drought, is certainly due to climate change. And I have to be honest here, this is a question that the climate community, for a single event, like a single drought, cannot yet answer with certainty. So I think I want to be clear here. People frequently make this sort of fairly casual leap from global warming to single events like this current drought. This is actually a subject of active debate in the community, and we're not going to make a statement that we can't really backstop. And we can't backstop the statement that this drought is demonstrably due to global warming. However, that said, we do know that major decadal-long droughts, like the event, and the event that we're now in is 4 years long, decadal droughts like this occurred across the West in the previous millennia. They're very common. We know that they occurred because we can look at lake beds which have trees all the way down to the bottom. These lakes are only fed by rainfall. So if this lake has trees, fossilized trees at the bottom of the lake, that means that at some point the rain stopped. And we know that we can find numerous lakes like that in the high ranges around to the east of us in California. We're also confident, and this is perhaps the most important message that I'm now going to segue to, that climate change is going to amplify these historical patterns. So this is one of the key messages I'd like you to take away from today, that even if a single event like the current drought is not necessarily due to climate change will exacerbate and amplify the tendencies for these events in the future. And these will become quite stressing events for the state water supply. So I'm going to start with the sort of the IPCC big picture, and then we'll narrow down to the West and to California through the National Climate Assessment. So this is the IPCC statements about the risk to the world's water supply. Changes in the water cycle. This means the natural water cycle where water comes from the ocean and from lakes, enters the atmosphere, then falls to the land again, runs off into the oceans and lakes, and then is replenished as a cycle. It's certainly going to change in a warmer climate. For reasons that are due to very basic physics, there's no way to avoid them. This is an unavoidable consequence of climate change in a warmer world. It is almost certain that the changes in precipitation will not be uniform. I'll come back to this point in a minute. What's going to happen, we think, is a very clear pattern, and it's a simple takeaway message. The wet get wetter, the dry get drier. We're in a dry part of the country. That means we're going to get most likely going to get drier for reasons that you'll see in a moment. The snowpack is going to disappear rather dramatically over the 21st century. And also, evaporation will increase. That'll be another reason why we're going to lose water. And the one thing we know almost for certain is that the snow cover is going to be severely impacted by global warming. So now let me drill down on those points. The basic message here is that climate change amplifies existing patterns. How do we know? We already see these patterns occurring in data. So this diagram is, again, taken from the IPCC Working Group 1 report, on which I was the lead author. All the arrows on this picture, which have little labels on them, for example, changes in ocean heat content, changes in air temperature, changes in water vapor, these are all copiously observed by multiple observing systems. So every arrow on this diagram represents a consensus of many, many lines of evidence that these aspects of the climate system are changing, and they're changing rapidly, and they're changing in ways that are historically unprecedented, at least over the observational record going back 1,000 years. So dramatic climate change, and these patterns are sort of, it's an amplification of trends in the climate system. One of the trends that's particularly important, and I'm showing you these are diagrams that are supposed to be sort of user-friendly from the IPCC. I'll be interested from your comments whether or not you think that they are. So the IPCC is sort of written for, essentially for ministers of climate and the participating countries from the UN General Assembly. The message behind this diagram is that the storm track that brings water to the West Coast through the Pineapple Express, those storm tracks in the Pacific Ocean that bring water to our shores, those storm tracks are moving northward. And they're moving northward very systematically. I'm going to show you that in the next diagram. We're not sure how this trend is going to play out over the 21st century, but what it does mean in general is that the areas to the south of us, for example, Mexico, are going to get systematically drier, and the areas to the north of us, like Canada and Alaska, are going to get systematically wetter. What's going to happen in California over the next few decades? It's a bit of a coin toss. But again, the wet get wetter, the dry get drier thanks to climate change. And I'm sorry for this diagram, I'll interpret it for you because it's written in scientific ease. But what this diagram is essentially saying is that the storm tracks are moving northward along the coast of California at the rate of tens of kilometers every decade. So play that out over the 21st century. The storm track in the Pacific Ocean that brings water to our shores is likely to move northward by at least 500 kilometers in the 21st century. The diagram, all the data points to the left of the dotted line are actually measurements from satellites, measurements from meteorological reanalyses of the present-day climate. So these trends come from present day, and this trend and movement in the storm tracks is predicted by extremely simple physics that's baked into the climate system. You can't dodge it, you can't avoid it, it's going to happen. So again, sorry for this flavor of the talk. I'm going to sort of work through the darkness before the dawn thing, and then we'll get back to, I think, some glimmers of hope toward the end of my talk. I don't really want to focus this diagram is extremely busy, but the main point of it is in the upper right-hand portion. There are many aspects of the climate system in which are still under debate, but one thing we're virtually certain on, and one thing that all the climate models agree on, is that we are due for much hotter temperatures. And those hotter temperatures, I realize this temperature scale is invisible. Under business as usual, the inner part of California is going to warm by probably 4 to 5 degrees, could warm by 4 to 5 degrees Celsius by end of century. To translate that into Fahrenheit, that's 7 degrees Fahrenheit. And that's going to be the norm. That'll be the normal change in the annual mean temperature. Heat waves under business as usual scenarios end up becoming what would be regarded as an unusual heat wave becomes the norm, and we actually expect what would be regarded as a stressing heat wave to be occurring essentially for 2 months every summer, every year. So what strange weather becomes the norm by the end of the 21st century. And those high temperatures, of course, increase evaporation from our lakes, from our water delivery systems that are exposed to air. And I'll come back to this point a little bit later because it ends up being kind of a stressing factor. Evaporation alone ends up being kind of a stressing factor for the water system. So the snowpack, we'll talk a little bit about how it's going to change sort of on average. This is some very nice but disturbing work by a colleague of mine, Noah Diefenbaugh, who's at Stanford University. And this gets back to this issue around the abnormal becoming the normal. This diagram, which I'm sorry for the small size, the diagram on the lower right-hand side is showing you how frequently the snowpack will be in March, so like the March we just left, will be lower than anything we've experienced over the last 30 years. And what the colors on that diagram show is that in California, extremely low snow conditions will occur every 3 years. So the abnormal becomes essentially the normal. It'll happen every 3 years. If you go up into the mountain ranges around in the state of Washington, it'll be occurring every 2 years. So they'll be experiencing extremely low snow conditions north of us. So the hope that we will be able to perhaps import our water over the border from our stateside colleagues north of us may be a bit of a false hope. This now is from the National Climate Assessment, and my colleague Mike Weiner is one of the lead authors on this assessment. This sort of shows you the impact on the water system mid-century. The color scale here, deep red is a 40% decline. So major declines in the water content in snowpack, major reductions in runoff, and you can see how those changes sort of hug the places where there are rivers in the state. So major changes in runoff from the Sierras, major changes in runoff along the coastline, declines of 40%, reductions in soil moisture, all of them occurring because of the reduction in snow. Now, the irony here is that California in toto may actually get more total precipitation. Why? Because a wetter atmosphere can hold more moisture. And that means that the additional moisture can fall on the land surface, but it will fall as rain, not as snow. And we've very much built our water system in the state, at least large portions of it, around the concept that snow acts as a time release mechanism for us. We bank the snow in the winter, we recover it in the spring and summer. It's been an incredibly valuable asset for us. That banking feature of the climate system is going to become stressed under climate change. So we may get more total water falling than state, but it won't be falling inside the perimeter of this bank. And that's one of the big challenges that we face going forward. And this is just sort of detailing this projected snow water equivalent decline again. This is broken out now by state and the contributions of each individual state to the total amount of snow water equivalent in the American West. So obviously states like Arizona don't play a major role. California and the states to the north and east of us do. These projections are showing declines by, on the order of about 60% by the end of century. This is under a business as usual scenario, and I should point out, by the way, that this business as usual scenario is actually under-predicting what we think climate change will be. The emissions, this is a scenario for how aggressive greenhouse gas emissions will be. This scenario turns out to be an under-prediction of how bad the rate of emissions increase is. So in other words, this is an underestimate of how severe the impact will be by end of century. And so this just says that, the water bank in the form of snow water equivalent is going to be, roughly 40% of what 40% of what we've enjoyed during this century. This has major impacts, particularly in the state of California. So this is showing, again, I'm sorry for the small font, but showing you the impacts in state. So what this diagram is showing you is that the San Joaquin River Valley, for example, has 40% less water in it by the latter part of the century. Ironically, other parts of the country will actually see increases in the amount of water inside their river basins, but we will face the impact of the lower banking of water, and that plays out both in the San Joaquin, the Sacramento, and the Klamath rivers by the end of the century. And again, this is all information coming out of the National Climate Assessment. So stream flow for the major river systems are projected to fall by north of 20% by mid-century, and even more by the latter part of the century. So that's surface water. The safety valve for this system for California has been another bank. This is a bank that is not being refreshed. It's being refreshed every year, but it takes much longer. The accretion rate takes a lot longer. This is groundwater. And we're fortunate to have some gigantic aquifers under, for example, the California Central Valley that we've been able to enjoy and use. Those systems are also under stress because they have to be replenished in order for them to be there for future generations to enjoy. And this is coming again from the National Climate Assessment a little bit later in the chapter that deals with with water impacts. So if you look at and they break out the water with use of groundwater sector by sector. If you look at the total withdrawals per square mile, California has one of the largest. It's something like 500,000 gallons per square mile annual usage over much of the state, and that's completely dominated by agricultural use. So about 80 to 90% of it is agricultural use. So we're definitely using the aquifer it's a particularly important bank. The challenge let me just deal with that banking issue for a moment. So that bank is replenished every year by rainfall and from water coming from rivers at the rate of about 2 million acre-feet per year. So that's the input into the bank thanks to Mother Nature. The withdrawals averaged over the 80s and 90s so the human withdrawals from that system were 6 times larger. They were on the order of 12 million acre-feet, with maybe 9 of that being put back thanks to losses from the agricultural system, with a net loss to the system of 1 million acre-feet a year. So you put in 2 from nature, withdraw 12, put back 9, net loss of 1. That rate of loss and depletion has increased dramatically in the recent past. So that's clearly not sustainable if you want the bank to be there in the future. And the other challenge that we face with respect to water withdrawals, and I'm coming down to my closing slides here, is that thanks to evaporation, so population, despite for a variety of complex reasons, partly because of substitution for humans into Central Valley in place of agricultural production, population growth alone is not expected to really greatly accelerate the stress on water withdrawals. But so that's what's shown in the left-hand diagram here. But once you fold in the fact that you're losing water thanks to increased temperature, you need more water to cool things, you're losing more of it to evaporation, you're going to significantly increase water demand just thanks to the fact you have a hotter climate. So all this is adding up to our 2 major water banks are getting depleted. You have a bigger demand thanks to higher temperatures. So that's what this is now is sort of a summary of the stresses coming out of the National Climate Assessment. It's just a reprise of what I've told you on the previous slides. So that's the challenge facing us. I think the question now facing the state is how do we move forward? One of the ways that we in the scientific community can work with the state, I think, is providing more actionable, more accurate projections of climate change. And I wanted to touch on that point in my last few slides and then turn to your questions. We are building some of the world's most advanced models for the present day and for the future climate. We were one of the first groups in the world to construct models, and this would have been an animation, but I chose just to show you as a still slide, that's able to project climate change down to scales of 25 kilometers. We're building models now that can resolve climate down to the scale of the width of San Francisco. We were shortly to have models that can project microclimates down inside the Bay of San Francisco. So this capability is coming online soon. We're testing these against the present-day climate. We are intensely interested in making these models useful to the state and would welcome the opportunity to deploy this capability in working with the state on understanding how climate change will affect our water supplies and what we can do about it. And the other thing that's riding to the rescue is the fact that this state has one of the most advanced technological bases in the world. We're bringing online computers which will allow us in the next 10 years to project climate. We can currently project climate down to scales of 200 kilometers, 25 kilometers now, 1 kilometer, so that essentially be able to resolve what's going on inside the city of San Francisco, for example, or between Sacramento and Davis by the year 2020. Quite a powerful capability. So the message I would like to leave you with is that there are opportunities for real and dynamic partnerships that involve an exchange of knowledge between the state, local entities, special districts, municipalities, state agencies, and the university and laboratory system. We're ready and willing to engage in that conversation. I think it'll allow us to harness the best research and technology available, essentially worldwide, to tackle the problem in state. I think we can be very smart about how we go about tackling this problem. And really what we're offering, I think, is both what we're offering is one of the world's best crystal balls about what could happen. That's what we're bringing to the table. And also a technological base and an interest in engaging with all the other citizens in the state of California on how to solve this problem, both to adapt and mitigate it. So thank you very much. I'd be happy to take any questions you might have for me.